All right, let's dive into a subject that's kind of secretly running the show behind everything from your weather app to the stock market. We're talking about probability. It's this amazing tool that helps us put a number on uncertainty and make sense of a world that is, let's be honest, pretty random.
I mean, think about it. You ask questions like this all the time. You check the forecast and it says there's, what, a 35% chance of rain? Well, that number, that 35%, that is a probability. It's our best shot at guessing what the future holds.
And it's not just the small stuff, right? Uncertainty shapes our biggest decisions too. When an investor is eyeing a stock, they're not just looking at what it did yesterday. They're trying to figure out the probability of it growing tomorrow, weighing that potential win against the risk of a loss.
And of course, we got to talk about the classic example, games of chance. Fun fact, the whole field of probability theory really got its start because some very smart mathematicians were trying to figure out the odds in gambling. It all comes back to, what's the likelihood this specific thing is going to happen?
This quote from Levin just hits the nail on the head. Probability isn't some dusty, abstract math concept. No way. It's a tool, a fundamental tool we humans came up with to deal with a world we just can't predict. It gives us a way to make smarter choices when we don't know what's coming next.
Okay, so if we're going to get a grip on how this all works, we first need to learn the lingo. Let's start with the three absolute core concepts, the building blocks of everything else.
First up, we've got the experiment. And no, this isn't about lab coats and beakers. In probability, an experiment is just any action where you don't know the exact result ahead of time. Tossing a coin? That's an experiment. Rolling a die? Experiment. Pulling a random card from a deck? You guessed it, that's an experiment too.
Okay, so for every experiment, there's what we call a sample space. Just think of it as the complete menu of everything that could possibly happen. So if our experiment is flipping a coin, the sample space is super simple, heads or tails. That's it. If we're rolling a standard die, the sample space is 1, 2, 3, 4, 5, or 6. It's the whole shebang.
And last but not least, we have the event. An event is the specific outcome, or maybe a set of outcomes, that we actually care about. For that coin toss, our event might be getting heads. For the die roll, maybe the event is rolling an even number, which, would include the outcomes 2, 4, and 6.
And here is where it all clicks together. Let's say our experiment is a bit more complex. We're tossing 2 coins. See that outcome column? That is our entire sample space. We could get 2 heads, a head then a tail then a head, or 2 tails. 4 possibilities total. Now, if we're interested in the event of getting 2 heads, we can just look at our list and see, yep, there's only one outcome that fits, HH.
All right, so now that we've got the basic words down, how do we actually put a number on this stuff? How do we calculate the odds of something happening?
Well, it really boils down to this one simple but super powerful formula. The probability of an event happening is just the number of ways it can happen divided by the total number of things that could happen. So let's go back to our 2-coin toss. What's the probability of getting 2 heads? Well, there's only one favorable outcome, HH, out of 4 total possibilities. So that's 1 divided by 4, a probability of 0.25. Simple as that.
And here's a key rule. Every single probability you ever figure out is going to land somewhere on this scale, from 0 to 1. You might see it as a fraction, or a decimal, or a percentage, but its value is always in this range.
So, what do those endpoints, 0 and 1, actually mean? Well, a probability of 0 means something is totally impossible. Like, what's the probability of rolling a 7 on a normal 6-sided die? It's 0. Can't happen. And on the flip side, a probability of 1 means it's a sure thing. I mean, for all intents and purposes, the chance the sun will rise tomorrow, that's a 1.
Okay, this is where things start to get really cool. We're going to look at how different events can be connected to each other, because they don't always happen in their own little bubbles.
You've got 2 big ideas here. First, there are mutually exclusive events. Think of them as opposites. If one happens, the other one absolutely cannot. You can't get both heads and tails on one single flip of a coin. Then you have independent events. These guys don't care about each other. The result of your first coin flip has 0, and I mean 0 influence on what happens in your second flip.
But what about when one event does mess with the odds of the next one? Well, those are called dependent events, and this card example is perfect. Imagine you have a full deck of cards. Your chance of drawing a queen is 4 out of 52. Pretty straightforward. But if you draw that queen and, here's the key, you don't put it back, You've changed the whole game. Now, for your second draw, there are only 3 queens left in a deck of only 51 cards. The odds have changed. The second event totally dependent on what happened first.
So, up to now, we've been kind of zoomed in, looking at one event at a time. But what happens if we zoom out? We start to see these amazing patterns in the randomness. That's where probability distributions come in. You can think of them like blueprints for how randomness behaves over the long run.
Before we can get into distributions, though, we need to quickly talk about the 2 main flavors of data they describe. First, you have discrete variables. These come from counting things, like the number of heads you get in 3 coin flips. It could be 0, 1, 2, or 3, but it can't be 2.5. Then you have continuous variables, which come from measuring. Think height, weight, time. These can take on any value in a range, decimals and all.
And that brings us to the king of all distributions, the one you've probably seen before, the normal distribution. You know it as the bell curve. This pattern shows up everywhere for continuous data. Things like people's heights, blood pressure, test scores. Its famous shape tells us something really profound. Most of the time, the results are going to cluster right around the average. And the further you get from that average, the rarer those results become. It's like finding a predictable pattern inside of randomness itself.
Okay, so we've talked about the lingo, the formula, even these big picture patterns. But let's bring it all back down to earth. Why should you care about any of this? Why does it actually matter in the real world?
Honestly, once you start looking for it, you see it everywhere. Businesses use probability models to decide how much inventory to stock so they don't run out or have too much left over. Scientists use it to figure out if a new drug is a real breakthrough or if the results were just a fluke. And of course, it's the engine behind weather forecasts, financial markets, and even your insurance rates.
And that's really the big idea here. Probability is not a crystal ball. It can't tell you what will happen, but what it does do is give us this incredible logical framework for thinking about uncertainty, for putting a number on risk, and for making the best possible call with the info we have.
It's all about equipping ourselves to move through this complicated world with a bit more insight and a lot more confidence. So the next time you hear a weather forecast, or see a stock prediction, or even just sit down for a game of cards, maybe you'll see the hidden rules of chance that are always at play. What are you going to look at differently now?